In section 17.1, we have derived the far field of the linear dipole antenna. Now we want to use the formula and then start our discussion on antenna pattern of the linear dipole antenna. So let's just copy down the antenna pattern function we just derived in the last session. And you see that this function is now depending on the angle and also the ratio of the antenna length to the radiation wavelength. So for example, let's pick up the half-wave dipole antenna as an example. For this example, the length of the antenna is equal to half wavelength. So you will expect that the current standing wave on this antenna rod will have a single standing wave lobe, and every point on this rod will have the same sign of the current. For example, you have the positive value of current at this point. You can also have the positive value of the current at this point. So this means that along the theta equal to 90-degree direction, you're going to have constructed interference. So no wonder you see the highest intensity radiation along this theta equal to 90-degree direction. But similar to the Hertzian dipole antenna, if you have the current oscillating along this direction, then you don't have radiation along this theta equal to 90-degree direction. We continuously look into antennas of different lengths. For example, this antenna has a length 2h equal to 1 wavelength. So this means that on this antenna rod, you will have 2 standing wave lobe for the current, because every standing wave lobe is going to be equal to half wavelength. And you can see that this current value is going to be in phase with the current value along this theta equal to 90-degree direction. So this means that along this theta equal to 90-degree direction, you will have the constructed interference from the subsections of the antenna rod. Therefore, you also see constructed interference along this theta equal to 90-degree direction. So basically, if you look into the far field and then sum over the radiation field from these 2 small antennas, the path will be the same. So this means that there's no phase difference between these 2 fields from these 2 antennas. But at the same time, the current phase, the phase driving these 2 antennas are also the same. Therefore, you have constructed interference along theta equal to 90-degree direction. Now, let's increase the antenna length to 3 half wavelengths. This means that you will have 3 standing wave lobe on this antenna for the currents. And in the far field, along theta equal to 90-degree direction, you're going to have destructive interference for the field generated from this plot, and also this plot. You can see their phase are 180 degree different. Therefore, the only field left for being constructed is going to be this purple part and also this purple part. So you can still have some radiation along theta equal to 90-degree direction, but the intensity is greatly reduced. However, along other directions, you can have the constructed interference. Therefore, along some directions, you have additional radiation lobe where you have high radiation intensity. Now, let's increase the antenna rod length to be equal to 2 times the wavelength. Then you have the 4 standing wave lobes on this antenna. Let's consider that in the far field along this direction, you can sort of divide this long antenna into 2 parts. And with the same distance from this antenna along this theta equal to 90-degree direction, just draw a line from this antenna and then draw another line from this antenna, and then you sum over the field to determine the total field in the far zone. And you see that this current wave has the phase 180 degree off this one. So you see that at theta equal to 90 degree direction, you don't have any radiation field along this direction. But along other directions, you could have constructed interference from the field from these two sub-antenna sections. So these three diagrams tells you that in the far field, the radiation intensity or radiation field is going to be the collective interference effect from different parts of the antenna. And the variation of the currents on this antenna is going to be quite important when you calculate the total field in the far zone. Now, I want to introduce the concept of antenna image. Suppose you have a quarter wave monopole antenna installed on this conducting material. And we learned about method of image before when we talk about static electric field. So think about when you have a charge move up along this direction, and because the current is moving up in this diagram, so we suppose there's a positive charge moving upward. The image of the charge is going to be negative, and the propagation direction of this negative charge is going to be downward. So this means that when you have a current moving upward for this section of the antenna, the image of the charge will create another section of antenna with a current also moving upward. So effectively, this quarter wavelength antenna on a conduction ground is going to be equivalent to be a half wave antenna, but the radiation field is going to be only in the upper half of the space. And this is the concept about antenna image. So you can use the solution from a half wave antenna to construct the solution for this quarter wave antenna on a piece of conducting material. Also, I want to define the so-called effective antenna length to simplify the discussion and also simplify the calculation. Let's first look into the solution for Hertzian dipole antenna. And you can see there's a term describing the direction and also the length. Then you compare this formula with the one we just derived for a linear dipole antenna. The comparable term will be this term where you have the direction and also the integration of the currents along the antenna rod direction, the z direction. So if you compare these two terms, then you can define a so-called effective antenna length given by this expression. Basically, you divide this with the maximum value of the current called I0. And then this is going to be, give you an effective antenna length. On the next page, we're going to see how we're going to interpret this effective antenna length. Suppose we look into the radiation field along theta equal to 90 degree direction. So this is a half wave antenna. And let's just set this theta equal to 90 degree. Then we reduce this expression to this one. And this one tells you that we can model this radiation with a short section of antenna with the effective length equal to LE with the current of I0 on this antenna. And this current is going to be a uniform current. So conceptually, it's going to be easier because the radiation field in the far zone along this theta equal to 90 degree direction can be considered as the radiation field generated by this simplified antenna. Well, similarly, we can also define the effective antenna length for a receiver antenna. For a receiver antenna, this antenna is going to receive an electromagnetic wave from far away, and the electric field of this signal is going to induce open circuit voltage on this antenna. So if you take the ratio of the open circuit voltage to the incident electric field, then you can define an effective length of this antenna. And sometimes the amplitude of the electric field inducing this open circuit voltage is going to depend on the incident angle. So if you take into account the incident angle, then the induced open circuit voltage is going to be equal to the effective antenna length given a direction dot with the incident electric field. And usually, if you derive a field expression for an antenna, the expression can have the field propagate away from this antenna or coming to this antenna. So the characteristics of receiver antenna and also transmitter antenna are the same, and this is called the reciprocity theorem for antenna. So you will expect that the effective antenna for receiver antenna is going to be the same as the effective antenna length for a transmitter antenna. 所以在这一小节里头，我们介绍了所谓的 antenna pattern， 同时我们也定义了 image antenna， 还有呢这个等效的 antenna length。那基本上呢，在一个线性天线里头，linear dipole antenna 里头呢，它有一个这个电流的 standing wave 在做这个辐射的激发。那这个standing wave 的这个 pattern 呢，影响到它原场的辐射的强度。所以呢，这个原场的 antenna pattern 呢，跟这个天线的长度相对于波长有很大的关系。但是在 θ 等于90度的方向上头，你不会有 radiation field， 因为我们知道在原场呢，这个辐射的方向跟电场的方向呢是互相垂直的。但是在这个天线里头呢，我们的电场跟我们的这个电流的方向都是沿着 θ 等于0度的方向，所以 θ 等于0度的方向呢是不会产生辐射的。那同时我们定义了这个等效的天线长度来简化一些讨论，也就是一个线性的偶极天线呢，虽然上面有一个电流随着位置是不一样的值，但是呢我们可以定义出一个等效的天线长度。那这个天线上头的这个电流呢是一个constant， 是一个常数。那这个可以用来就是简化一些计算跟观念上的这个介绍。所以呢，这个是17.2节里头所介绍的一些观念，供您参考。谢谢。